Before. Good afternoon, Mike. Before I do begin, I did put. I put the not this, but this assignment, which is going to be due Thursday. I did say I would leave up answer any questions if you had any. If you were getting stuck anywhere with the definite integral, we're going to do more integration today. So, you'll be able to see it. We'll be doing some more definite integrals, so you'll be able to see how to do some of these. But if you attempted any of these and you got stuck, now is the time to kind of ask, and we can kind of do that. If there's any specific questions on any of them on the first page, and it looks like I did number 7 on the other page. So there's only 6 to do, and then the challenge one, of course, is just that, a challenge one. See if anyone can attempt that. But if there are no specific questions on those, I'll go right to the next section of the notes. All right. So nothing specific. So you still have till Thursday. You have Thursday to hand it in. Again, we'll do this again on Thursday. And if any questions arise from there, feel free to ask on Thursday, since none are coming up today. All right. So now we're going to get into the integration of absolute value functions, because these are a little bit weird, and we knew with at least with differentiation, you couldn't differentiate absolute value functions, not easily. If you remember, if you differentiate an absolute value function, just kind of refresh our memory. So here is coordinate plane. Remember, our absolute value functions looked like just a v. And the problem with differentiating, taking a derivative of them, was the point right here. There's an infinite amount of tangents right there. We cannot take a derivative right there, even though it's a continuous function. So the derivative kind of looked like this. The slope of the left line was negative, so there was like an open circle here, and there was something like, it looked something like that. That was the derivative of it. And you'll see the 2 open circles on the y-axis because of that point right there. It's not differentiable at that point. We're going to have a similar problem when we start talking about integration. Because if you can't differentiate it, how do you go backwards? How do you antiderivative something that wasn't differentiable in the first place? So that's kind of where we're going to be going with this. And ultimately, there are going to be solutions that we're going to be able to do. Because remember what an integral is, especially this definite integral from -2 to 3. There's an area that can be accounted for, added up, and so forth under this curve. In fact, these areas are actually a little bit easier because the areas under these curves are going to be shapes we're used to, triangles. And that's something we can certainly deal with. But when you know how to do the method of integration, it's going to be far easier than doing triangles. It's going to seem easier doing the triangles because this first example is easier. But when we get to more complex ones like this, even just adding something plus or minus from the actual absolute value, that's going to make a big difference. We're going to see exactly why. But first, we're starting off with a relatively easy one. Normally, I would put this in a graphing calculator, but we should be able to graph this anyway. Because of the minus sign inside the absolute value, that actually shifts it to the right, not to the left. Usually we think, oh, -2, it shifts to the left. It's actually shifting to the right. So the vertex of the absolute value function is actually right there. And the slope is going to be plus 1, minus 1. So one of the absolute value functions looks like that. And the other one is going to look like that. And this is f of x equals the absolute value of x minus 2. Now let's think about what we're actually going to be doing here. We're taking the integral from negative 2 to positive 3. So let's look at where negative 2 is. That's right here. To positive 3. 1, 2, 3. Right there. Now, we're looking for the area under this curve. Now, this is the first time we're able to do this with an integral. This doesn't happen very often, because usually we're taking the integral of something that's a curved line. But these have distinct shapes that we know how to take the area of, which are just two nice triangles. You can even, triangles, pretty straightforward. 1/2 base times height. So we're actually going to find the answer first, then we're going to do the integration method to figure out how to do that. Well, like I said, we're not going to be doing this area method all the time. That was triangles, because it will get a little bit more complicated, especially when this whole thing, what happens if you just shift it down just a little bit and the vertex is somewhere weird, and then the areas get definitely a little bit more complicated. Even just shifting it down just half a unit really complicates things. So the method we're doing right now is not the traditional one, but it is going to give us the right answer. Well, this triangle is 1, 2, 3, 4. This triangle is also 4 units, right? 1, 2, 3, 4. So 4 times 4 is 16, cut in half. The area to this triangle to the left is 8 units. And then this one is a 1 by 1. And 1 times 1 is 1/2. So 8 plus 1/2 is 8.5. So hopefully, when we do our integration method, we get exactly 8.5. Let's see. It says, with the function you graphed, you can easily calculate the area under the curve of the given intervals since none of the lines are curved. We just did that. We found it to be 8.5. Now it says, without a graph, we will use integration. In order to start, we must determine that an absolute value function is a set of two linear equations. For the absolute value of x minus 2, what are the linear equations? So they're talking about these equations right here. If you look at this line right here, what is the equation of this line right here? Well, the equation of that line is just, what is it, x, or negative x plus 2. How do I know it's negative x plus 2? Well, I'm using the basic rules of a line, y equals mx plus b, that you learned in 9th grade. The slope is negative 1. The y-intercept b is 2. So one of our equations is y equals negative x plus 2. Then what about this line right here? What's the equation of this line? Now you'll notice a small problem. This does not intercept the y-axis because look where it is. But you have to imagine, what if it were to keep on going? Even though it doesn't, where would it go? Well, it would intercept right at negative 2. I know it's negative 2 because usually one of the functions is just the original. So x minus 2 is this one right here. So that's the other one. Y equals x plus 2. However, these are, they end. It's a piecewise function, in other words. So if you remember piecewise functions, an absolute value could be written like this. We have negative x plus 2, but only when x is, in this case, less than or equal to 2. And the other one would be x plus 2 when x is greater than or equal to 2. You'll notice there's there's two different equations, and I put a less than or equal to both. That's because when x is 2, oh, sorry, there should be a minus. That's because when x is exactly 2, you should get 0 for both of them, so it doesn't matter which one you use. Hopefully that's pretty straightforward. But now we're going to use these linear equations and integrate both of them on their appropriate intervals. So remember the original problem was this. Integrate from -2 to +3 the absolute value of x minus 2 dx. So what we're going to do is we're going to integrate two equations. So we're actually going to split it up into two integrals. But we're also going to use the correct intervals that we're using. So I'm going to start from left to right. So the left part of the equation is my green line here, the -x plus 2. So I'm going to integrate -x plus 2 dx. But what am I going to integrate over? So the things that's changing are what I put up here and here. Well, you always have your starting point, and our starting point was -2. But what's the top part going to be? Because this part of the function never actually goes to 3. It actually ends right at +2. So instead of integrating it from -2 to +3 like we're supposed to, the green part of the function only goes to +2. So we're only going to integrate from -2 to +2. But then we're going to add in the other integral, and this is where the 3 is going to come from. We're going to use the other function, which is x plus 2 dx. But this integral, well, this one, it starts right where the other one left off, at +2. And what number do we want to go to? We want to go to 3. So when you finish your problem, your entire interval should be these two right here, -2 and +3. And these two numbers typically should be exactly the same. It picks up where the other one just left off. So now what we've done is we've broken up the integral into two parts. And what's really cool about it is this integration should be exactly the result of the first triangle, which we knew to be an area of 8. And the right-hand side should be an area of +1/2. And then it should add up to exactly what we want. So that's basically how we do absolute value functions. You break it up into two integrals, and then you integrate. The hard thing is figuring out the new intervals. So I'm going to take my antiderivative. So this is -1/2 x squared plus 2x evaluated from -2 to +2 plus 1/2 x squared plus 2x evaluated from 2 and 3. So remember what this notation means. You got to do the top minus bottom for the definite integral. So I'm going to try to squeeze everything down here. So top minus bottom. I'm going to plug in 2 first. Definitely get used to brackets, parentheses, and so forth, because now that you're doing two integrals, evaluating two definite integrals, don't lose track of negatives. We know we should get 8 for the first one. We should get 1/2 for the other one. So -1/2 times 2 squared plus 2 times 2 minus the bottom one, -1/2 -2 squared plus 2 times -2, close brackets. So all of this was the top minus bottom here. Now I got to add in the other integral. So it's plus brackets, top minus bottom. So 3 squared plus 2 times 3 minus, let's see if I can squeeze this last one in. The bottom is 2, so it's 1/2 2 squared plus 2 times 2. Now I'm really out of room, but let's see if we can finish this problem. I'm going to go through the arithmetic a little quickly. That's a 4. This should be a -2, because that's 4. 4 times -2 or sorry, 4 times negative 1/2 is negative 2. Add them together, you get 2 minus. This is 4, positive 4. Again, you get to negative 2. Plus negative 4, so minus 4. So this is negative 6. Plus. That's 4.5 plus 6, so 10.5. Minus 4, so it's 2, plus 4, so it's plus 6, or minus 6. Just double checking. I think I made a mistake somewhere. Let's see who can find my mistake. Oh, let's see. I definitely made a mistake somewhere. Ah, I made it really early too. These are the two functions. So I've made a minus sign error. It's not too big of a deal. It should be easy to fix. I apologize for making that error, but minus sign errors are probably the most common. So you'll notice that this is the function and this is the one that I wrote. So the error is actually right there because the original function should be x minus 2. And the other one is, so the first one is correct. So all of this is fine. So where is the mistake? This minus sign, that should be a minus, because this should be a minus. So this actually might be a little easier to correct than I thought. So that becomes a minus, that becomes a minus 2x. That means this becomes a minus, that becomes a minus. And then from there, we'll just recalculate. Recalculate that. Now that should fix it. 4.5 minus 6. That should be a minus. 2 minus 4. So it's negative 1.5. Plus 2. Yep. Because this is negative 2 minus, so it becomes plus 2. And that'll fix everything. So I apologize for making that mistake. But wasn't too bad to correct. I just had the wrong equation written down. You're going to notice the left-hand side, the equation in purple, is 8, exactly what we had expected. So this is equal to 8 plus negative 1/2 plus 2 is 0.5, which is 8.5. Exactly what we should have expected right from the beginning. So we did get 8.5 twice, which is exactly what we wanted. Obviously, the bottom is going to be definitely more complicated. The geometric version is easier, but it's not always going to work out that easily. We're going to do one more where the geometry of it is easier, but we're going to do it in reverse order. We're going to do the hard way first, and then we'll do the easy way to check. So we're going to take our integral of the absolute value of x plus 4, and we're going to try not to visualize it. We're going to try to think about what the equations are, and then from there figure out where to go from there. And then we probably won't get to it today. We'll probably do it on Thursday. We'll take a look at, well, what happens when that absolute value function shifts up or down. Then there's really no good way to check. Checking geometrically is not going to be nice. But let's see if we can do this one. So first thing I would do, if you have trouble visualizing the graph in your head, try to sketch one, put one on a graphing calculator. I know I have this graph section down here, but I'm going to try to avoid using it. I'm going to try to do it based on sketching rather than graphing it exactly. So just remember what an absolute value, what the plus means right here. It shifts it to the left form, not to the right, because it's plus. When the things are in parentheses or in absolute values, it shifts it to the other direction. You can easily prove that to yourself by throwing it in a graphing calculator, that the point to the v is going to be right there. That way you get a sense, okay, what are the two equations right here? And it's really easy to figure out. One is always that, x plus 4. And when you look at it, you should be able to determine which one is the x plus 4. It's the one with the positive slope. It's the one to the right. Well, what's the other one? Well, it's always the negative to it. So you can always just take this, basically an absolute value function, x plus 4. Both linear functions are just the plus and minus of it. So it's super simple. You just negate the other signs. So the other equation is negative x minus 4. And you can see that's true with this one as well. This was negative x, this is positive x, this is positive 2, this is negative 2. So everything is just flipped in that case. And you were going from negative 6 to positive 3. So we got to think about, well, which function is on the left? This one is to the left. So that's the one you want to integrate first, because that's the one that's most to the left. So you'd go from negative 6 to where? Well, you go right to where you hit that v part of the graph, which we know this v part is at negative 4. So the first integral we're going to do is we're going to integrate negative x minus 4, because that's the left part of the graph, dx. We're going to integrate that from negative 6 to negative 4. And then that part of the function is done. Then we're going to do the right-hand side. So it's plus the integral of the other one, the right-hand side, which is x plus 4, dx. And remember, this one's going to pick up where the last one started off. So you're going to start at negative 4. And then up at the top, wherever you want to end up, which our answer says, well, our question says, we want to go to positive 3. And that is your setup right there. So I think the last one, I think I made it seem a little bit more complicated than it actually is. But I mean, step 1, take the absolute value function, take the positive of it, the negative of it, figure what's on the left, what's on the right, integrate both, figure out your intervals. And then the rest is just a definite integral that we can integrate from there. So the bottom part is, hopefully I'm not going too quick with the antiderivative, but I think these are numbers that we have seen so many times that they should be easy. Oops. So negative x is going to be negative 1/2 x squared minus 4x. Taking the antiderivative, and I put the big bar, negative 6 and negative 4, plus 1/2 x squared plus 4x, the bar, from negative 4 to 3. I guess technically I should put these in parentheses because I want to evaluate the whole function. And then the plug-in. Be careful with your plug-in. Definitely make sure you give yourself a lot of room. Top minus bottom. Negative 1/2 negative 4 squared minus 4 times negative 4 minus the bottom. Negative 1/2 negative 6 squared minus 4 negative 6. I think that's my top minus bottom of this right here. Just gonna double check. There was a lot of negatives there, so I want to make sure I didn't miss any. Lots of negatives there though, so we'll have to be careful with that. Plus top minus bottom here. 1/2 3 squared minus 4 times 3. That's the top. Minus the bottom. Oh, wait, that should be a plus, right? Because of this plus. Yep. Minus the bottom. 1/2 negative 4 squared plus 4 times negative 4. A lot to squeeze in. And let's see. I'll take my time with this one because of all the negatives. So this becomes 16 cut in half by a negative. So this should be negative 8. Negative times a negative. It's going to be a positive, so it's plus 16. Minus 36 cut in half by a negative is negative 18. Negative times a negative is a positive. Plus. This one's nice and easy, actually. Even though it's a decimal, but that's fine. 9 cut in half is 4.5. Plus 12. 16.5. Minus 16 cut in half by a positive is 8. Minus, because it's positive times a negative, 16, so this should be negative 8. Continue going. You get 8 minus 6 plus 16.5 plus 8. And I'm going to actually do the left-hand side because remember, that should be the first triangle. This should be the second triangle. So I am going to write, it's not necessary, but I am going to write 2 plus 24.5 because I think it gives you a good idea. When we check our work, the left-hand side triangle should be 2 and the right-hand side triangle should be 24 and a half. And it does make sense that that right number is much bigger. Look at the intervals. This one was only 2 apart. So that triangle is definitely smaller. It has a smaller base. But look at the other triangle. It goes from negative 4 to 7. That triangle is much bigger. That has a base of 7 units compared to only 2. So the fact that we're getting a much bigger number for one triangle compared to the other should make sense. We get 26 and a half for our answer. And now we're going to use the geometry version to double check our work. All right. So it says use the graph to check the area. Well, we already know 1, 2, 3, 4. It goes right here. Here's 1. I'm going to try to redraw that because I may have missed one. I think I definitely did. We're going to integrate this from negative, what was the integral? Negative 6 to positive 3. So 1, 2, 3, 4, 5, 6. Here's negative 6 to positive 3. 1, 2, 3. So just take a look at the two triangles that you have. Is it so far becoming reasonable for that to be an area of 2 and this to be an area of 24 and a half? I think so far, yes, it is. We're going to double check. Now that we have the triangles, we're going to figure out the base and height to each of them, and then again apply 1/2 base times height. So this is a 2 by 2. This triangle is a 1, 2, 3, 4, 5, 6. This is a 7 by 1, 2, 3, 4, 5, 6. That's a 7 by 7. And now we're going to do 1/2 base times height. 2 times 2, cut in half is 2. Exactly what we got up here for the first integral. And then the second integral, 7 times 7 is 49. 49 cut in half is exactly what we'd expect. 24.5. Exactly the value we would want right there. Then lastly, we could add them together and get 26.5. Again, I know, and I said at the beginning of the stream, you might be thinking, why would we use the integration method when that's far more complicated? There's so much room for error in that method when this seems basic. My geometry kids can figure out the area of these two and then add them together. That's easy, much easier. But it is going to get slightly more complicated when we now bring in this new one, which we only have 8 minutes left, and I know these take a lot more time. I am going to end it a little bit early because I don't want to jump, I don't want to have to stop in the middle of one. I know I'm not going to have enough time to finish this entire problem. But this one is going to show you why we're going to need that. I am just going to graph it really quickly, and then hopefully you get a sense of why the integration method is going to be required and why we can't really rely on the other method. So if I'm integrating this, it's x plus 3, so that means here is where the v part would want to be, but because of that minus 2, and that one's true, that's a true translation, the v actually ends up being right here. And then we would graph it like normal. Slope of 1, so it would be here, here. I don't like that. That's better. And then this one on this side. And so far all our slopes have been 1. It's still just the number in front of the x. If it were 2, I'd be going up 2 over 1. I don't want you to automatically think that, oh, all absolute values just go up by 1 over 1. It still matters what's in front of the x. So now our function looks like this. And we want to graph this from -9 to +3. So problem number 1, -9 is, I believe, off the graph. Yep, -9 is over here. To +3. 1, 2, 3. So now when we consider the area under the graph, what's the area, because now you have this section. What about this section in here? That's technically under the graph until you get to the point, and so forth. So you can see that the geometry behind this is going to be a little weird and a lot more difficult to do because you could bring this over. You could figure out the area of the whole triangle very easily, but you remember, negative areas count, and you can't just add up the areas. You got to take the negative areas, compute it with the positive areas, and then do the same thing with the other triangle that's going to be over here. That would go up to whatever this is and this, because really what you have are 4 areas. This one, which these seem simple enough to figure out, but then you get these shapes that are trapezoids that you would need to figure out. So you have these 4 areas, and you can make it even more complicated by taking the trapezoids and making more right triangles, figuring out all the bases and heights to everything, and that's going to be, I think, a lot more time consuming than the actual integration of it. And that's what we're going to get into on Thursday. Is we're going to figure that out. We're not going to do the geometry method. We can still visualize it and help us figure out what it's going to look like, but this is ultimately what we're going to be doing. All right. So I'm going to leave you right there. Don't forget, you still have the assignment. You still have these 6 questions. Remember, you can come on Thursday. I'll answer any questions that you do have, and then you can hand it in anytime on Thursday. All right. But we're going to end it right there. We're ending a little bit early, but that's fine. But I'll stick around for about a minute. If you have any questions, just type them in chat. If not, I'll end the stream. I am going to turn my mic and the video off, but I will stick around. If you type anything, I'll turn them right back on. All right? You guys take it easy and enjoy the weather. It's real nice out today.